Absorbance and Fluorescence Lab. Our problem in this lab was to identify unknown samples using absorbance spectrums that we construct and also to create an emission and absorbance spectrum for fluorescein, a known fluorescent dye. The main ideas we used were calculating absorbances of solutions to identify given unknown samples. We used different unknown samples to create the absorbance and emission spectrum, that being fluorescein, and then we can also understand that light can be modeled three different ways, as a ray, a wave, and a particle. Our goal was to use spectroscopy to both identify the absorbances and concentration of unknown samples and to calculate an absorbance and emission spectrum for fluorescein. The initial experimental design was to attach an ocean optic spectrometer to our computer. We would then shine the flashlight through one side of a cuvette with our unknown sample in the cuvette, with the spectrometer probe on the other side directly across from the light. We would then compare the sample wavelengths with a control wavelength, that being water, and then calculate the absorbance using our known equation, using log base 10 of I naught over I to calculate absorbance. I is intensity. We can then use this to calculate the concentration using the known equation that log base 10 intensity naught over intensity equals epsilon times path length times concentration. We can manipulate the equation to solve for concentration. Second part of this experiment was to take the fluorescence of fluorescein, a known fluorescent dye, by placing the flashlight at 90 degrees to the cuvette and measuring those rays that came out. We would also repeat the first step of the process by getting an overlapping wavelength. We would then obtain the absorbance spectrum and the emission spectrum for fluorescein and create this wavelength versus absorbance versus emission graph to overlap the fluorescence curves. Now, just to define some terms before proceeding on, we can define transmission as the fraction of light that passes through the sample. We identify fluorescence as the light emission that is from a different wavelength than the previous sample due to electrons falling from an excited to the ground state. We can use absorbance as the amount of light that is absorbed by the sample, and concentration as the molar concentration of the sample, calculated through finding absorbance and path length.
Two different calculations were used for this lab. One calculation that was used repeatedly was to find the absorbance from the intensity and wavelength using A equals log base 10 of IO over I, where IO is the intensity of water and I is the intensity of the dye. An example calculation was done for the fluorescent dye at wavelength of 340.985 nanometers, and that equaled 0.00208. We also calculated the concentration of the dye solution. This was done by taking the log base 10 of IO over I. This came to 4.12 times 10 to the negative 6 molar. And this concentration was calculated using the peak absorption wavelength of the dye. Here we compare our graph of the orange sample of absorbance versus wavelength compared to the given wavelengths versus absorption for the Lapidus dye and Sawtelle dye. The unknown dye was determined to be the Lapidus dye. The peak of our dye was closely related to that of the Lapidus dye, which we were given from the known spectra. The Lapidus dye had a peak around 550 nanometers, and our unknown dye has a peak around the same wavelength. The Sawtelle dye, however, had a peak around 475, which is not similar to ours. The next graph that we have is the absorbance graph versus fluorescein versus emission graph. So here we had to scale the absorption peak by a scale of 100 times to fit it on the same plot. But as you can see, the red graph shows the emittance from the fluorescence, and it is a lower energy than the absorption, so it is shown to be at a higher wavelength.
We can identify an unknown sample by using an absorbance spectra by comparing the spectra of the unknown to a known absorbance, much like what we did on our lab. The concentration of a substance can be calculated using Beer's law, which is shown on the slide. Absorbance spectrum measures the amount of light absorbed at a particular wavelength, while fluorescence spectrum shows the amount of light emitted by a particular particle after it was originally excited by another photon of light. The critical difference between the two is that the absorbance only measures the wavelength that are being absorbed, while fluorescence measures what wavelengths are being emitted from the particle as it's losing energy. A particular practical use of absorbance for red gas analyzation, which is used to identify presence of pollutants in the air. Fluorescence spectra, on the other hand, is growing highly in the medical field as a way to identify microorganisms in the gut. In fluorescence, a different wavelength goes in than what comes out of the original of the molecule. The excited molecule jumps up to a higher level of energy and oscillates there until it starts to lose energy, at which time it comes back down to ground state. When it comes back down, it has less energy, and since energy and wavelength are correlated, this causes the wavelength to be different. Overall energy is still conserved because the difference of energy from initial excited state to when the molecule comes back down can be explained by the oscillation that occurs at the higher energy state. During oscillation, energy is lost to the environment since this is a open system and the remaining energy is shown in the new wavelength as it fluoresces. During our setup, we needed a dark environment because the optic cable is sensitive to light and we did not want to pick up outside light sources to disrupt our data. The light source must be at a 90-degree angle from the optic cable because during the recording of our emittance, we did not want any light being picked up from the flashlight itself. Potential sources of error. One potential source of error we had is that sensors could be picking up light from other sources in the room, such as the windows, since they were not fully covered. Another source of error is keeping the light source and the dye and the sensors in the same position from each trial.